Noble gases. Noble gases belong to the 18th group in the periodic table. The noble gases are also called as inert gases or rare gases. Because these gases are non-reactive, they are also called as inert or noble gases. Their shells and subshells are completely filled and thus they have very stable configurations which can be related to their chemical inactivity. The noble gases are also considered as rare gases because they represent not more than 1% of air. Their electronic configurations are like of helium 1s2, neon 2s2, 2p6 and so on. Among these gases, except radon, all exist in atmosphere. Radon is an element generated through radioactive process and can be produced by the radioactive decay of radium and thorium minerals. Cavendish in 1784 for the first time separated a mixture of noble gases. Rayleigh in 1894 discovered argon and it was the first among the noble gases to be discovered. Neon, krypton, and xenon were discovered in 1898 by fractional evaporation of argon under varying reduced pressure condition. Radon was discovered by Dohn in 1902 as a radioactive disintegration product of radium. The name of noble gases derived from Greek words and their meaning is helium, helios, neon, new, argon, lazy or inert, krypton, hidden, and xenon, stranger. Helium is present in the atmosphere at a concentration of 5 ppm and can be obtained from natural gas deposits. The most abundant noble gas is argon. Argon is produced by electron capture of potassium. Uses of noble gases or inert gases. As helium has the lowest boiling point among the noble gases, it is used as cooling gas in nuclear reactor and also as a carrier gas in gas liquid chromatography. It is also used in stereoscopy. Helium is also preferable over hydrogen in airship due to inflammable nature of hydrogen. Helium is also preferably used to dilute oxygen in gas cylinders in place of nitrogen for divers. This is because helium is slightly soluble in blood while nitrogen gas is more soluble in blood at high pressure and causes painful conditions in patients. Noble gases including neon are used in discharge tube to give different colors. Argon is used in welding stainless steel, metallurgical processes of aluminium, magnesium, and titanium. Argon is also used in electric bulbs, fluorescent lamps, etc. Radon is used in the cancer treatment due to its radioactive nature. General characteristics and uses. At ordinary temperature and pressure, all noble gases are monoatomic gases except radon. They are chemically inert but under certain conditions they can form complexes. These gases are colorless, odorless and tasteless. The other general properties are explained below. Atomic radii. Their atomic radii are very large because of the radii are van der Waals radii or non-bonded radii. Atomic radii of element increases from top to bottom in a group. Melting point and boiling point. Melting and boiling points of noble gases are very low because interatomic forces are very weak in these gases. Electron affinity. Due to completely filled electronic configuration, the electron affinity of these gases is zero. Enthalpy of vaporization. Enthalpy of vaporization is very low because the forces between the atoms are very weak forces, that is van der Waals forces. Ionization energies. The ionization energies is very high because they have very little tendency to accept or lose electron. Physical properties. Adsorption. All noble gases can be adsorbed on charcoal at low temperature and the order of their absorption is xenon followed by krypton, argon, neon and helium. Diffusion. all noble gases have a tendency to diffuse through glass, plastic, and rubber materials. Therefore, it becomes difficult to work with them in the laboratory. The order of diffusion depends upon their size, which is as follows: helium, followed by neon, argon, krypton, and xenon. All noble gases have high electrical conductivity at low pressure and thus can produce characteristic colored light during electric discharge at low pressure. Liquefaction. Due to the van der Waals forces, these can be easily liquefied. The liquefaction depends upon their atomic size. The order of age of liquefaction of noble gases is: the most liquefiable gas is xenon and the least is helium. Solubility behavior. All noble gases are less or sparingly soluble in water. The solubility is due to dipole induced dipole interaction and increases from top to bottom with increase of the size of atom. Therefore, the increasing order of their solubility is xenon followed by krypton, argon, neon and helium. Abnormal behavior of helium. Among noble gases, helium shows abnormal behavior. It has some different properties from other group members. Helium gas on cooling below minus 269 degrees Celsius changes to liquid. Helium on further cooling at minus 271 degrees Celsius and at 1 atmospheric pressure changes to a liquid which has high thermal conductivity. Helium can be contained in solid from under high pressure while all the other noble gases solidify on cooling. Helium has a tendency to flow upward. It acts as superfluid. Chemical properties. The atoms of inert gases have completely filled shells and therefore they are chemically inert. Under certain specified conditions, they combine and form some rare compounds. Compounds of noble gases. Compounds formation under excited state condition. These types of compounds are formed by helium. At low pressure, in the presence of mercury, tungsten, etc., helium forms HgHe2, HgHe10 and WHE2. One electron from 1s orbital of helium excites and goes to 2s orbital. This excitation costs about 460 kilocalorie per mole energy. These compounds are also called halides, which can survive only for a moment and can be detected spectroscopically. Compound formation through coordination. Noble gases have electron pairs in their valence orbitals. In the presence of strong electron deficient groups, noble gas compound can be prepared through coordination. That is, among noble gases, argon forms a number of unstable compounds of the type Ar.XPF3, where X is 1, 2, 3, 4, 6, 8, 16, which can be easily dissociated at their melting point. Compound formation through dipole-induced dipole interaction. The inert gases such as argon, krypton and xenon can form compound with water through dipole-induced dipole interaction at low temperature and high pressure. These compounds are known as hydrate. For example, Ar.6H2O, Xc.6H2O. Compound formation through physical trapping. That is clathrate formation. The inert gases such as argon, krypton and xenon can form solid compound with certain organic molecules such as phenol and hydroquinone under a pressure of 10 to 40 atmosphere. In these compounds, the noble gases are trapped into the crystal lattices or cavities formed by organic molecules. The organic substances that form the cavities are called the host, while the atom of noble gas is entrapped or enclosed in it, it is called the guest. Thus, it is also called as guest-host interaction. In this compound, the guest components are held together by van der Waals forces. Hence, there is no chemical bonding involved in these compounds. This is a kind of physical interaction. It is not necessary that all the activities in the host lattice are filled. Thus, the clathrate are also used as non-stoichiometric compound. These weak interaction can easily be broken and inert gas atom can escape from the host by simple heating the crystal or by dissolving them in a suitable solvent such as alcohol. For example, clathrate can be prepared by crystallization of an aqueous solution of quinol with argon, krypton or xenon under a pressure of 10 to 40 atmosphere. The smaller noble gases like helium and neon do not have tendency to form clathrate compounds because they are too small to fit in the cavities and can easily escape from the cavities. Synthetic zeolites can also form cavities in which heavier noble gas elements can fit easily. Clathrates are very useful categories of compound because they can store radioactive krypton and xenon produced in nuclear reactor. Compounds of xenon. Preparation. The first noble gas compound XCPTF6 was prepared in 1962 by the reaction of PTF6 with xenon in equal ratio at room temperature. PTF6 plus xenon gives XCPTF6. Further, reaction of XCPTF6 with PTF6 at 25 degrees Celsius gives XCF positive and PTF6 negative. Xenon reacts directly only with fluorine to form xenon complexes. However, oxygen compound can be prepared from the xenon fluoride. Xenon reacts directly with fluorine at 400 degrees Celsius in a sealed nickel vessel, and the final product depends on the xenon fluorine ratio. Xenon plus fluorine in the ratio 2:1 gives xenon difluoride, and the ratio 1:5 gives xenon tetrafluoride, and in the ratio 1:20 gives xenon hexafluoride. Properties. The compounds xenon difluoride, xenon tetrafluoride and xenon hexafluoride are all white solids. They sublime at room temperature and can be stored in nickel containers for a long time. The higher fluorides can be prepared from lower fluorides by heating with F2 under pressure. First, all the xenon fluorides are strong oxidizing agents. On reaction with hydrogen, they reduce themselves to xenon. In similar manner, they oxidize I negative to I2, Cl negative to Cl2, Ce3 positive to Ce4 positive and reduce themselves to xenon. Like xenon difluoride plus 2HCl gives xenon plus 2HF plus Cl2. Second, all the xenon fluorides are strong fluorinating agents. They fluorinate the other metals. Like xenon tetrafluoride plus 2SF4 gives xenon plus SF6. In the above reaction, XeF4 is fluorinating sulfur. Third, in organic synthesis, xenon difluoride is commercially used in synthetic organic chemistry. It does not react with alkyl or aryl groups of organometallic compounds but attack, oxidize or fluorinate only the heteroatom in the organometallic compound. That is CH3I plus XeF2 gives CH3IF2 plus xenon. Similarly, C5H55 plus xenon difluoride give C6H5IF2 plus xenon. In the presence of anhydrous HF, its reactivity increased and it may be due to the formation of XeF positive. That is, platinum plus xenon difluoride in presence of HF give PTF6 plus xenon. Reaction with water. All the fluorides have different reactivity with water. Xenon difluoride reacts slowly with water and reduces itself to xenon. Xenon difluoride plus water gives xenon plus HF plus oxygen, while xenon tetrafluoride violently reacts with water and forms xenon trioxide. Xenon hexafluoride also reacts with water violently. On reaction with atmospheric moisture, xenon hexafluoride form highly explosive solid xenon trioxide. Xenon hexafluoride on partial hydrolysis form colorless liquid, that is xenon oxytetrafluoride. Preparation of other xenon compound. Xenon trioxide is an explosive white hygroscopic solid soluble in water. It reacts with xenon hexafluoride and xenon oxytetrafluoride to form xenon oxytetrafluoride and xenon dioxy difluoride, respectively. That is, xenon trioxide plus xenon hexafluoride gives xenon oxytetrafluoride, and xenon trioxide plus xenon oxytetrafluoride gives xenon dioxy difluoride. Xenon trioxide forms xenate HxCO4 negative and perxenate HCO64 negative in alkaline solution. Perxenate ions also react as strong oxidizing agent and oxidize HCl to Cl2, water to O2, and Mn2 positive to MnO4 negative. Perxenate ions form volatile and explosive compound xenon tetraoxide on reaction with concentrated sulfuric acid. Complex formation: xenon difluoride, xenon tetrafluoride, and xenon hexafluoride have tendency to form complexes with BF3, GF4, SNF4, PF5, ASF5, SPF5, and PTF5. In these complexes, fluoride acts as fluoride donor. The complexes are XeF2.MF5 give XeF positive, MF6 negative. Similarly, 2XeF2.MF5 give Xe2F3 positive, MF6 negative. Similar complexes are formed with ASF5, PF5, SPF5 and BF3. Compounds of xenon. Xenon forms a large number of compounds as compared to the other noble gas element because ionization potential decreases from helium to radon. Among these, helium, neon, and argon are inert, and krypton, xenon, and radon are noble. The structure and bonding in different xenon compound is discussed in this section. Structure and bonding in xenon compound. First is xenon difluoride. Xenon difluoride is linear in shape having 3 lone pair of electrons. In the atom of xenon, one pair of electron of p orbital gets unpaired and one electron is promoted to d orbital. Then central xenon atom undergoes sp3d hybridization with trigonal bipyramidal orientation of 5 sp3d hybrid orbital. The hybrid orbitals with lone pair of electrons take equatorial position. The remaining 2 orbitals with single electron in each take axial position and overlap with p orbitals of fluorine atom. Due to the presence of lone pair on a plane, its geometry appears and is linear. Xenon tetrafluoride. In xenon tetrafluoride, the central xenon atom is sp3d2 hybridized and 6 sp3d2 orbitals should be present on the 6 corners of the octahedral geometry. But due to the presence of 2 lone pairs of electrons at axial position, its actual geometry becomes square planar. Next is xenon hexafluoride. The central atom in xenon hexafluoride is sp3d3 hybridized and the geometry should be pentagonal bipyramidal. But due to the presence of one lone pair of electron, its geometry becomes distorted pentagonal bipyramidal in which the lone pair of electron pointing through one of the faces of the octahedron. Xenon trioxide. In xenon trioxide, the central atom xenon is sp3 hybridized and due to the presence of one lone pair of electron, its geometry becomes pyramidal instead of tetrahedral. The 3 unpaired electrons promoted to d orbital form 3 p-pi d-pi bonding with 3 oxygen atoms. Xenon tetraoxide. In xenon tetraoxide, xenon atom is sp3 hybridized and the geometry is regular tetrahedral. There are only bonded pair of electrons and no lone pair of electrons present in the structure. All the xenon oxygen bonds are double bonds, that is p-pi d-pi bonds in xenon tetraoxide. Xenon oxytetrafluoride. In xenon oxytetrafluoride, xenon atom is sp3d2 hybridized and geometry of the molecule should be octahedral. But due to presence of one lone pair of electron, its geometry becomes square pyramidal. One xenon oxygen double bond is p pi d pi type. Xenon dioxide difluoride. In xenon dioxide difluoride, the central atom xenon is sp3 dehybridized, and due to presence of one lone pair of electron at equatorial position, its geometry becomes butterfly shape. The two xenon oxygen double bonds are p pi d pi bonds. Next is perxenate ion. In perxenate ion, the central atom xenon is sp3d2 hybridized. Hence, the geometry is octahedral. The two xenon oxygen double bonds are p pi d pi types. Theories of bonding in xenon compound. There are four theories for defining bonding in xenon compound. Ionization potential based theory. Hence, due to lower ionization potential of fluorine, it can attract an electron of xenon towards itself and form Xz positive F negative. The first bond is ionic in XzF2. Thus, it becomes very difficult to attract second electron of Xz positive because second ionization potential of xenon is very high. Hence, second bond will be covalent bond. Hence, xenon difluoride can show the two resonating structures. Second, valence bond theory. According to valence bond theory, there are two covalent bonds in xenon difluoride. The structure of xenon containing xenon compound can be correctly defined by VBT. Third, molecular orbital theory. There are some limitations of valence bond structure of xenon difluoride. These are due to the large size of 5d orbital, overlapping is very weak. According to valence bond theory, atomic orbital of same energy can overlap. While in case of 5p and 5d orbital of xenon, the energy difference is 960 kJ per mole. Hence, overlapping cannot occur easily. However, MOT can easily explain polyatomic bonding in xenon difluoride molecule. Three atomic orbital linearly combine to form three molecular orbital. Bonding involves the 2p Z orbital of 2 fluorine atom and the 5p Z orbital of xenon atom. Because of bonding to occur, only orbital with same geometry must overlap. Out of the 4 electron, the 2 electron occupy bonding molecular orbital, and this pair of electron is responsible for binding all the 3 atoms. The rest of 2 electron occupy the non-bonding molecular orbital. Because the non-bonding orbital have more fluorine character as compound to xenon character. These electrons are situated mainly on 4 fluorine atom. This type of bonding is 3 center 4 electron pi bonding, sigma bonding, that is 3c minus 4e. The following linear arrangement of the atom gives the best arrangement with its observed structure. The structure of xenon tetrafluoride can be understood in similar way to that of xenon difluoride. The 5px orbital of xenon forms a 3-center MO with 2pz orbital of 2 fluorine atom, just as in XzF2. The 4py orbital of xenon forms another 3-center MO involving the other fluorine atom. Thus, the two perpendicular 3-center MOs are formed, which give rise to square planar geometry to xenon tetrafluoride molecule. The MO theory cannot explain the structure of XzF6 because 3-center MO system that are perpendicular to each other would give a regular octahedral geometry, but the shape of XzF6 is caped octahedral. Thank you.